It was beginning of gas chromatography, and we had already made it very clear what is gas chromatography, and we started with the advantages of gas chromatography to begin with, and we said that it is very time saving. The separation is over within a few minutes, and then it is sensitive, it's reliable, it is versatile, and whatever. So these were the attributes of gas chromatography which was discovered on the basis of suggestion made by Sinch and James in 1941. And as I said yesterday, the first gas chromatograph came in 1960. And the popularity, we said yesterday, of GC was because of these attributes, especially the versatility in sensitivity and reliability and vast nature of analysis. And then we saw a block diagram of a gas chromatograph. It is the instrument. We saw block diagram, and we discussed different parts: the carrier gas, its characteristic feature Y, and then the injection port, its characteristic feature and Y, and then column O1, and then the column inside, and then the detector and the chart, step chart record to record the chromatogram for qualitative and quantitative analysis. And we said that the temperatures of the injection port, of the O1 and hence the column, and of the detector are independently controlled electronically within plus minus 0.1 degrees Celsius. It is that accurately controlled. And then we said that the temperature of the O1 is the same as temperature of the injection port, but the temperature of the detector, which is very highly sensitive and expensive part, nothing to condense into it, so at minimum 20 to 50 degrees it is kept at a high temperature compared to the temperature of the O1. Now today we will see, in fact I have changed my presentation completely today, so make it relatively easy. Yes, please. Now, the most striking feature of gas chromatography is that substances having the same vapor pressure at a given temperature, same vapor pressure, can be easily separated by appropriate selection of liquid phase. Because we did mention yesterday that carrier gas does not play any role in gas chromatography in bringing about separation. It just acts to carry the solutes from one end of the column to the detector. Its role is O1. And so main function inside the column of bringing about the separation of solutes is done by the stationary phase. Now when we talk about distillation, we have seen that if two liquid solutes have almost the same boiling point, both of them will be distilled off. So separation is very, very difficult. Unlike that, when you talk about gas chromatography, two solutes may have the same vapor pressure, but when they pass through the column, they get separated. Why they get separated, we'll see step by step. And it is only because even in the vapor state, those having same vapor pressure have different interactions with the stationary phase. And as a result of that, one moves ahead, the other solute remains behind. The major advantage of GC, therefore, over distillation is the ability to use selective solvents, where I mean the meaning of solvent in this presentation, please note it down carefully. In the GC presentation, whenever I talk about solvent, it is the stationary phase, stationary liquid phase. Yeah. And we are going to see what are the different liquid phases which can selectively separate solutes in the gaseous phase. Now we said that two solutes may have the same vapor pressure and still get separated. Why? Because there are different types of interactions of solute molecules with the stationary phase. For example, the four interactive forces which can aid in the GC separation is orientation forces. That is, forces resulting from the interaction between two permanent dipoles. The hydrogen bond is a particularly important type of orientation force encountered in gas chromatography. I will tell you. Let us see that we have these two types of compounds. Okay? Hypothetical. And the other one is with OH group. This is X, so that it should not be mixed up with benzene. It's not benzene. But X group, which doesn't have any OH group. The other solute has OH group. And we find that both the compounds have same vapor pressure. But what is the difference between them? The difference between them is one is having OH group. So with the stationary phase, there is hydrogen bonding of the second solute. As a result, it is retained by the stationary phase for a longer period of time compared to the first solute. So first solute is eluted first, and then the hydrogen bonding is broken subsequently by the carrier gas flowing, and then the second solute comes in. So this is what is the forces resulting from the interaction between two permanent dipoles. So the stationary phase has a dipole, and so also this OH group, and therefore through the hydrogen bonding, one solute is retained more compared to the other one which does not have hydrogen bonding in the stationary phase, and therefore two solutes having almost same vapor pressure can be separated effectively by gas chromatography. The second one is induced dipole or divide forces. For example, forces resulting from the interaction between a permanent dipole in one molecule and induced dipole in the neighboring molecule. These forces are usually very, very small. So we need not bother about this, but we have to remember that divide forces also may contribute. We'll take examples subsequently, but divide forces which play very small role, but still they contribute towards the separation of two very similar solutes on the basis of their differences, minor differences in the dipole. Now dispersion or London forces is called. What are they? Forces arising from synchronized variation in the instantaneous dipoles of the two interaction species. These forces are present in all cases and are the only source of attraction energy between two non-polar substances. They are weak compared to A and B. So B itself is weak compared to A, and compared to A and B, C is still weaker. So we are talking about some attractive forces between two non-polar solutes. It's very difficult to have, but then theoretically it has been proved that yes, they have. And therefore, these forces are very, very weak. And therefore, we need not consider them very seriously. and the partition coefficient, that is specific interaction forces resulting from chemical bonding complex formation between solute and solvents. These forces of interaction determine the solubility and thereby the separation achieved. Their combined effects are expressed by the distribution constant Kc that we know. Kc is nothing but amount of solute per unit volume of liquid phase divided by amount of solute per unit volume in the gas phase, and the value of Kc is high when most of the solute is retained in the liquid phase. Obviously, because in the liquid phase, if it is more compared to the amount of solute in the gas phase, the Kc value as defined will be very, very high. So out of these four forces, the hydrogen bonding, the Debye forces, the interactions between two non-polar solutes, and the solubility. Out of these four, the first one and the fourth one are the predominant forces responsible for bringing about separation of solutes in gas chromatography. The first cause, hydrogen bonding, requires the presence of hydrogen OH bond or COOH bond, COH group in the molecule. Whereas the solubility factor, the fourth one, doesn't require the presence of OH. It just depends on how much A solute is soluble in the stationary phase compared to B, so that one spending more time in the stationary phase will have longer retention time compared to the one which spends most of the time in the gaseous phase. And this Kc, which is the distribution between the liquid phase and the mobile phase, as we know, transport is negligible in the liquid phase. We know that when the solution is in the liquid phase, it doesn't move ahead. And only that fraction in the gas phase is carried out. We have explained this earlier also. Thus, separation between two solutes is possible if their distribution constants are dissimilar. Obviously. So you may be realizing now that whatever we have discussed during theory of chromatographic separation is being repeated, almost repeated here. And that is the beauty of first learning the theory of chromatographic separation and then going to the specific applications of separation by GC or by other techniques of chromatography. Yes. By the way, did you see two? So I think I will bring them in the class. She had a very interesting question. She said, I am not clear about what is the difference between packed column and capillary column. So fortunately there was a time gap and my research student was there. So I told the research student to take her to the GC instrument and actually show her how does a packed column look like and how does a capillary. And I always believe seeing is believing and handling is confidence with your own hands. Looking at this and handling makes a hell of a difference, right? So packed column has a larger diameter wherein we can put in the stationary phase, either an adsorbent or a liquid coated stationary phase, whereas in the capillary or open tubular columns, we cannot do that because of its very small diameter. So they come in the form of fused silica capillaries where the inside are coated by 3 degrees. It could be a liquid, it could be a porous material, or it could be a solid of small particle size coated with a liquid but still bonded with the walls, so that the central part of the column remains open, so it is open tubular column. Prakash, why don't you go and bring illiterate? I'm trying to learn many things, but then my expertise only is up to writing email, sending and receiving and opening the email so far. I can't make PowerPoint presentations also. But then I have an array of research students, so I can call anybody, request, and then one secret I have to share with you, and that secret is whatever animations we have shown and we will be seeing are not made by me. Two persons are responsible for that. I will introduce to you both the persons maybe by Saturday. They are expert in doing this. One is my past PhD student, Simran Kaur Mathur, and the second one is Professor Ajit Kumar. So they are experts in doing this. I tell them what I want, and they incorporate that there, and I proudly present that in the class to make your ideas very clear. Yes. So solvent efficiency. Solvent means again the stationary phase is nothing but ratio of the separation factor. Separation factor is x2 upon x1. Now in this graph, a very interesting thing you will notice that I have measured retention times from time 0, and I have also measured right from the peak of air, which is my reference point. Normally, in practice, you will measure retention times always from the peak of the solvent. Now here mobile phase is air, so air gives a peak. You will ask me why? You say that air is completely free from impurities. Now so ever you try to purify air, it is 99.9999 maybe, but still that 0.001% impurities are there, and that impurity helps us because it gives a small peak along with the air, and that we use because air is first to come out. The nitrogen or the carrier gas is first to come out. So with that, if the impurity is there, then that is the reference point. Okay? Right. So next one is, please remember this one, the distribution constant Kc, which we have defined earlier. Show that again, distribution constant, earlier slide. So distribution constant is amount of solid per unit volume of liquid phase divided by amount of the same solute per unit volume in the gaseous phase. Correct? Remember this, and then the next statement. Yes. See, the distribution constant, the third statement, fourth statement, the distribution constant decreases with increasing temperature. Why? Because as the temperature increases, from the stationary phase, solutes move into the gaseous phase. So the concentration in the gaseous phase increases, and that in the stationary liquid phase decreases, and therefore the solutes move faster, and therefore their retention times are reduced in gas chromatography with increase in temperature. And it is generally found that the retention time is halved. If it is 10 minutes, it becomes 5 minutes if temperature of the column is increased by 30 degrees. It is approximate observation, but yes, if you increase the temperature by 30, the retention time is reduced to 1/2. Contrarily, if you decrease the temperature by 30 degrees, the solute increases twofold. Then, this results in decreased separation since it is the liquid phase which performs the separation. Because if you are disturbing the Kc by increasing the temperature, the solute which was moving earlier faster is immediately followed by the other solute because it is getting separated from the stationary liquid phase and going into the gaseous phase. So it means that the other effect of increase of temperature is also decrease in the resolution. Please remember this carefully. In gas chromatography, if you want to improve resolution between two peaks, you have to decrease the temperature of the column. Because it is made very clear that by increasing the temperature of the column, the Kc decreases, meaning thereby the amount of solute molecules in the gaseous phase increases and therefore resolution decreases. I repeat that. Just listen to me carefully. I am saying that since the separation of two solutes in gas chromatography, which we are considering at this point, depends on the distribution of solute between stationary phase, it could be an adsorbent or a liquid, we are talking about a liquid, and the gaseous phase, which is a carrier gas. And the way Kc is defined, we are talking about the amount per volume of solute in the liquid phase divided by that in the gaseous phase. So higher the concentration, let us say, of solute in the liquid phase, higher will be the value of Kc. Now when temperature of the column is increased, it helps solute molecules in the liquid phase to go into the gaseous phase. So your denominator increases in Kc. So Kc value decreases, right? And therefore, the conclusion in gas chromatography, if you increase the temperature, the resolution becomes relatively less. If you want a better resolution between two neighboring peaks, you have to decrease the temperature at the cost of increasing the analytical time. Okay, next. Therefore, to achieve better separation, lower temperatures should be used. Lower temperatures mean more liquid phase interactions, more separation, but longer analytical time. And at a minimum, the solute should spend 50% of the time in the liquid phase so that the retention time exceeds twice the retention time of air. Therefore, the carrier gas. But the most important thing is to achieve better separation, lower temperatures should be used. Lower temperatures mean more liquid phase interaction, more separation, and longer analytical time. Next, please. Yeah, you can skip this. Okay, show that graph, please. Yes. We have seen this how to calculate using the equation. Final equation I have given is n is equal to 16 into Tr upon Tw bracket square, to simplify. We did not go into the derivation of that equation. Yes, we have seen that yesterday, characteristic of carrier gas, because this is a separate, another simpler presentation, send it to some presentation. Inert, yes, dry and free from impurities. This also we have seen. Yes. The effect of water also we have seen yesterday. Yes. Next. Now we said that flow of carrier gas has to be kept, or it should remain constant throughout our separation experiment. If it doesn't, then experiment to experiment, the retention times will vary. We don't want that to happen. And in order to achieve a stable flow of carrier gas, we must have a little valve. So it is so delicate that you can adjust within plus minus 1 milliliter per minute. And that too, it has to be reproducible. As I said yesterday, if she stops the experiment and you continue again, you should be able to reproduce that flow rate to reproduce the retention times. Reproducible, and it should not be a very laborious process to get the reproducible flow. It should be very convenient. And you will, when you go through, please insist on showing how the gas flow is controlled. In the laboratory, you see the traps, and then you will also see, they will open with GC for you to show different parts and ask them to show how the flow is regulated. Okay. Now, effect of decreased flow rate. We know that. The graph shown in bold line, it with the X flow rate of mobile phase, that is carrier gas. However, if it decreases, naturally the retention times of solutes also will increase. So the dotted lines, A is shifted to higher, B shifted to higher retention time, and C in fact has gone beyond. So very obvious, we have seen in that switch experiment also, that if there is decrease in the flow of mobile phase, then there is also increase in the retention time, because Ux, we said, is directly proportional to U. Yeah. Yeah. Now the reverse way. If the flow rate increases, see all the peaks are eluting near the solvent, that is in fact so close to the solvent peak that it is not acceptable to any chromatograph, not at all. So we shift by decreasing the flow. This is the example where I said in gas chromatography, decreasing temperature or decreasing flow rate increases resolution. So temperature and flow rate both work in the same direction. If you increase the temperature, resolution becomes less. If you decrease the temperature, resolution improves. Similarly, if you increase the flow rate, see what is happening? Overlapping peaks you are getting. But if you decrease the flow rate, you are getting beautiful baseline separation. Right. We have seen this rotometer, but it's a colorful picture in this presentation. That's all. Yes. We have seen this temperature must be maintained of the inlet, that is injection port. We said it should be made up of a material which is chemically inert, so that it doesn't interact with the carrier gas, it doesn't interact with the solvent in which solutes are dissolved, and it doesn't react with the then it should be, volume should be low. Why? We see an inert construction also. Next. This also we have seen yesterday, but see it again. Back column and capillary columns, and now I will pass on these two columns, but please be careful about handling the capillary one. It's very, very delicate. I kept it in a box. Nevertheless, you please see. This is a stainless steel tube. One end goes to the injection, other end goes to the detection. So solute mixture passes through this heart, and then separation is brought about, and then detection is done. So you can see the diameter of the column, and you can also see capillary. This is the capillary column, and when you see the packed column, you will be able to see the difference in the diameter. can skip this. We have seen this. Let them complete the round of. See, maybe you can stop for some time. See carefully. Take class you know, just have a look. And when you see these two, you want to see them simultaneously? I think that will be a good idea. Please give me that. So that, you know, this is the camera. See the diameter. Awesome. You have seen that? You have not seen? What's that? तो कितनी स्ट्रांग है वगैरह पकड़ो तो स्ट्रांग है स्टेनलेस स्टील सा है बाहरी पकड़ो पर हाफ आवर वीक है see the relative difference in the diameter and one advantage of capillary column is that you can have a capillary column of minimum 25 to 30 meters to 100 meters or maybe 150 meters because it's a small coil. This is also a coil, but it's a bigger coil, and so the length of the packed column does not normally is more than 1 meter in the form of a coil. This may be 2 meters, but not more than that. Because in some institutions you may not be able to see even a gas chromatograph, but at least see the columns. Injection syringe तुम्ही बघितले आहे ना सगळ्यांनी but on a micro, this is in microliter. Normally our injection syringe is in milliliters. You are scared of having injectables, na? You have seen that advertisement, 1 minute, 1 minute. Right? Have you seen that? Sardarji is refusing to have injection. This part is over. Please bring this back. Okay. Okay. Now we have to introduce sample so that the moment we introduce sample, if it is gaseous, it immediately goes onto the column. But if it is a liquid, then it is dissolved in a vaporizable solvent. So the solvent vaporizes, which gives the first peak. Solvent peak, you have seen this. And then instantaneously also, all the liquid solutes or solid solutes are vaporized, and in a one plug they go onto the column with the mobile phase, carrier gas. Now, because you have seen this difference in the diameter of capillary column versus the packed column, you will immediately realize that you cannot use the same injection system for all the columns. Now this alone costs about 20,000 rupees. This. So like a cylinder, that's an injection syringe, but it is only how much? 10, 15, 20 microliters. So you dip this in the solution, and then very delicately you have to pierce the needle into the septum, okay, and then delicately introduce the sample. This also in the box, I will keep it here. So handle, boys especially handle, like you will handle a delicate girl. At least you can imagine. Okay, chalo. So next one. Now the almost as important as column choice is the choice of injection, because if you are not in a position to introduce sample, what is the use of a very delicate and sophisticated column with stationary phases? No. Throw it. Very small. Okay, next. So you have to realize that introduction of sample is as important as the column itself. And the various approaches are mentioned below. Number one is direct injection. When it is packed column, you can direct injection with the syringe. But if it is capillary, then you have next. In this case, the solvent is evaporated before injection, resulting in improved separation of fast eluting. Then the sample is introduced into the column as a liquid, reducing sample decomposition and giving reliable. There are very specific cases where samples are thermally highly labile if they remain at that temperature for a longer period of time. Next. Okay. This we have seen yesterday. It's weightless, quick injection, and with the help of the syringe. Now, column we have seen is thermostated inside the oven, and because the temperature has to be kept constant, and two types of analysis are possible. Yes. ISO means same. Thermal, same temperature. It means that throughout your separation experiment, you keep the temperature of the oven constant. Fix it 100, 150, 200, 250, whatever you want, and don't change it. So that method of GC separation is called as isothermal gas chromatography. But imagine, and I want now answer from you for this question. Imagine that one solute in your sample has a boiling point of 100 and the other has 200 degrees Celsius. And you have kept, what temperature will keep of the oven? Let us say you will keep 100. So the first solute will get eluted. What about the second? Huh? No, we are talking about isothermal. So if we are doing isothermal with two solutes having distinctly different boiling points, at 100 degrees, the second solute may not have enough pressure, vapor pressure to come out. So it just won't come out. Okay, then somebody will say, keep the temperature at 200. Very good idea. What will happen to the first solute? Zoom. So almost next to the solvent it will come out. Would you like it? No. And therefore, if there are 10 such solutes with 10 variable temperatures, it is going to take longer period of time for separation, and we cannot afford it. So we have another way to solve this problem. Yes, next. This is called programmed temperature. The column temperature is increased linearly with time. For example, and there is a program, you don't have to do it manually. You program it that your to begin with, your temperature of the oven will start at 50 degrees, and then you increase the temperature because you know the boiling points of all the solutes. So you say that up to 110 degrees per minute. After the first solute is eluted, then make it 15 or 20 degrees until it reaches the next 10 minutes to 100. And therefore, the entire analysis, which was taking much longer time in isothermal, can be done through temperature programming in a shorter time. Next. Next. Yes. See here. Now the figure 1 shows the elution pattern of the components at a constant column temperature of 150 degrees Celsius. The lowest boiling compound emerges close together. Here, I'm just saying. They are not separated. And the higher boiling compounds are not eluted from the column, as I said, with two solute examples. On the other hand, on the right hand side, we have programmed temperature between 50 and 250 degrees at 8 degrees. I don't know why 8 degrees. I would have kept it either 10 or 5. But 8, fancy. See, all the solutes are beautifully separated in 36 minutes. Just 36 minutes. And up to 95 minutes here, all the solutes are not separated. So this is a great advantage of temperature programming in gas chromatography. Just like in liquid chromatography, we said there are two modes of separation: normal mode and reverse mode. Reverse phase mode, normal phase mode. Similarly here, very rude comparison that isothermal at the same temperature and temperature program separation. Next. Okay, what should be the nature of stationary phase? If you remember, I had made a mention of coating of a suitable liquid on the surface of inert solid support. Now we will talk today of what is that suitable liquid phase, especially in gas chromatography. Now that, you remember the principle? Light dissolves light. This applies here also. So what is it has to be a good absolute solvent for sample components. It means that all components must dissolve readily in that liquid phase. So one of the conditions in choosing is first find out what is the nature of solutes. If it is non-polar, then you choose a liquid phase which is non-polar, because in that phase only it will act as a good solvent for all the sample components. Then that particular solvent must also show differences in solubility for the components present, the solutes present in the sample. If it doesn't differentiate between solute A and B with reference to solubility, they will not be separated. So this is the second condition which a mobile phase or stationary phase must satisfy. It has to be chemically inert, obviously. Then a large specific surface area from 1 to 20 square meters per gram. It all depends on the particle size again. Smaller the particle size, larger the surface area. And pore structure, it has porous in nature, regularly shaped particles, which is ideal. I mean, I said that it is not possible to get exactly regularly spherical particles. So, like we discussed in general discussion, we want a liquid that will dissolve all the components of a mixture, which will demonstrate differences in the solubility towards the components present in the mixture. And Also, it could be coated on such particle size where large surface will be available, and that particles will be porous in nature. Yes. And of course, mechanical strength. I mean, suppose a gas moves under pressure, the particles of the stationary phase and hence the mobile phase should not be fragile. It should not break. So the mechanical strength of the stationary support on which liquid is coated has to be very strong. Okay. This we have seen. No, not seen. Okay. Basically, hold on. Basically, choice of stationary phases becomes very easy because they are classified under non-polar liquids, polar liquids, and speciality, highly speciality stationary phases, liquid stationary phases. Yes, one by one. Non-polars are obviously hydrocarbons. Next, alkyl silicon phases, they are also non-polar, and polar substituted silicon phases where polar groups are introduced, therefore they become polar. If no polar substitutes are, then they are non-polar. Then ester phases are polar. Next, and polyether phases are also polar in nature. Speciality are high temperature phases. Hold on. Sometimes you require a stationary phase to separate solutes at, let us say, 350. Not always, but some solutes are there which can be separated only at that high temperature. Now, if you want to separate at that temperature, your liquid phase must be thermally stable. It should not have vapor pressure at that temperature. Otherwise, along with the solutes, the vapors of the stationary phase also will come out. In fact, that is one of the requirements of all stationary phases, liquid stationary phases, that under operating temperature conditions, they should have bare minimum vapor pressure. Otherwise, what will happen? The process of bleeding, what is called as bleeding. If the stationary phases are volatile, then with the temperature increase, they will be removed, and that process is in chromatography is known as bleeding. We don't want that bleeding to happen. And especially when high boiling solutes are there, we have to select a stationary phase which at 350 degrees will have minimum vapor pressure. Also, chiral phases. There are mixtures of chiral solutes, and these phases cannot separate them. So you have to have speciality chiral stationary phases. And lastly, it is the liquid crystalline phases also for specific applications. In short, therefore, we have three types of liquid stationary phases. The non-polar one with specific examples, the polar one, and the high speciality stationary phases. But all of them have to satisfy the previous conditions. We'll repeat those conditions, previous one. Because, go back. Go back. Previous slide. Now you will appreciate. Good absolute solvent, good differential solvent, chemically inert, large specific area, surface area, pore structure, regulatory shape, mechanical strength, and as I said, that the vapor pressure under experimental temperature condition should be minimal. And all the choice, therefore, will depend on what? Suppose you want to choose out of next. Now these are the phases in front of you. I have given you a sample containing, let us say, 5 solutes. How would you choose one of them? You have to choose one of them, na? How would you choose? What would you ask me? Yes?
Nature of solute.
Nature of solute. Right. Then in GC, we are doing by GC.
Boiling point.
Boiling points. तो what else can I do? पीछे कौन बोला? बहुत बोला रे. So, right, boiling points. Anything else? She said, na, nature of solutes. So it is polar, it is for the central part. If it is non-polar here, if it is speciality, you have to go to. If you have to have parallel liquid phase or high temperature or liquid crystalline phases also are extremely useful. So we'll take a break of 5 minutes and then come back for the remaining discussion. See the column, see the syringe. Syringe, don't try to touch. This capillary column, don't try to touch. Which I always call. One by one, because I don't know your numbers, I will call you. The person will come here and answer simple questions. So today's next section is that which will also help you as a revision for the Saturday test. Now, since I had worked in Ruya College for 34 long years, I will start with Ruya. Ruya, roll number 1. Is he or she there? Yes, please come. Don't be afraid. If you are wrong, I am there to correct you. I am not here to criticize you or let you down. Please remember this. That is not the aim of any teacher. Yeah, please introduce yourself.
My name is Abigail Baptista. I'm doing my MSc in Bioanalytical Science.
Ruya. Tell me, how would you define chromatography?
The separation technique that is based on the method of adsorption and part.
Okay, in a way, see what she said, chromatography is a technique or method of separation in which, yes, solutes are phenomena of adsorption or partition is involved. Do you think, yeah, please speak. Yeah. Do you think it is a complete definition? Or does it need any improvement? Yes?
It's a separation and identification of the solutes in the mixture on the basis of phenomena of adsorption and partition.
Okay, good addition. Yes. Good addition. If I say following, let us see whether we can still modify that. So it's one of the separation techniques, because there are solvent extraction and other things. One of the separation techniques in which a mixture of solutes travels across the surface of a stationary phase along with the mobile phase and through the processes of either adsorption or partition or ion exchange or size exclusion, solutes get distributed between the stationary phase and mobile phase and separation occurs. And after separation occurs, it can be, each solute can be qualitatively and quantitatively analyzed, as she says. This need not be the only definition. You can write and modify your definition so that it will be crystal. You can refer to reference books, as I said. You can borrow books from our laboratory. We have plenty of them. I have personal books also. You can, the Khalsa students especially, can borrow books from my personal library and from my KB. But chromatography is one of the techniques of separations. When you say one of, the other thing has to be plural. Huh? One of my friend name, sir. One of my friends. One of my many friends. So one of the techniques of separation, where solutes in a mixture move across the stationary phase along with the mobile phase. They get distributed between stationary phase and mobile phase depending on their degree of absorption or partition or ionic exchange or size differences, and after they are diluted, they are qualitatively and quantitatively analyzed. Okay. Do you agree with me? Ruya 17. Present? No. Okay, you can stand there. Don't worry. Don't bother. Now, what type of question you would like me to ask? You frame a question. See, please remember here, framing a question is more difficult than answering a question. You frame a question. I'll give you 1 minute for framing a relevant question on our topic. Please sit down. Ruya, 15? 15. Okay. Now you can come here. Introduce yourself.
Hi, my name is Rumi Sharma and I'm doing MSc Bioanal from Ruya College.
What are the different forces which are responsible for separation in gas chromatography?
There is first one was Thiessen forces, which was due to the specific common dipole interactions. Two common dipole interactions. Example is hydrogen bond.
Okay.
Then there were D-by forces, that was between a permanent dipole and a neighboring non-polar, and the third one was between two non-polars due to
What's the most important?
fourth one was chemical bonding, that was difference in their solubility
Between
between the stations.
You have to be specific. See why I am doing this exercise, because on Saturday when you answer, you have to be specific. Don't have to be vague. You cannot afford to be vague. Number one, you have to be a good listener, in a sense that you should listen to the question properly so that your answer should be pointed. Right? Suppose I ask you, where do you come from? So she said, there is one place in Uttar Pradesh. Uttar Pradesh is part of India. You know that. Yes, I know that. Then there is a district and district. What should be the crystal clear answer? Come on, where do you come from?
Haryana, Pali.
A place called Pali from state of Haryana in India. In India. This is a specific answer, right? Okay, thank you. Yes. Khalsa College number 1. Introduce yourself. So this exercise will also decrease your pressure. Sir, marne rahe ho. This is, and it will increase your level of confidence.
My name is Adarsh Gupta. I am doing MSc Part 1 in Bioanalytical Science from Khalsa.
What did you find most significant in Mikhail Sweig's experiment? Mikhail Sweig conducted one experiment. So what was striking to you the most in his experiment?
Separation of
Separation of what? separation of but what is the specific answer? Separation of 5 complex solutes from chlorophyll would be the right answer. That struck me the most. Right? Why the name was given as chromatography?
Because the bands of different colors.
Yeah.
Sequence.
Yeah.
So it appeared to him as a color band.
Yes. And
So
so
he gave the name.
color writing is chromatus is color.
Means color.
Chromatos is color and graphene is writing. Therefore, so would you use this chromatography term for colorless solute separation? Classification of, yes, question is framed. Good. Read out if you want. I don't mind.
So what would be the causes of band broadening?
Yes. What could be named? What
What
are?
the causes?
What are main causes? Because we are not discussed, and it's not possible also to discuss all causes. But what are the major causes for band broadening? Where? In chromatography separation. In chromatography separation. Right? Okay, tell me one.
It's the approximate spherical shape.
What are the major causes, you said? Nah? Your question is that. So when you have framed the question, you must have answers in your mind. So your multiple path flow, which is also called as eddy diffusion, is major cause. Right? Another cause, mobile phase mass transfer, stagnant mobile phase transfer, and stationary phase mass transfer. Is it not a revision? Right? So you also know how to frame question precisely and how to answer also precisely. Because at this MSc level, and our TYPSC students also, please know that the examiner is a human being. If he reads vague answers, paper after paper after paper, he gets irritated or she gets irritated. And then you feel, oh, I had written everything and why did I get only 60 marks? I was expecting 80 marks. Fortunately, now it is internal assessment 40%, so you have every chance to score maximum there through attendance, seminar, class test. So this could be, on Saturday it will be a class test, which will be part of your 40% evaluation this year. Right? Can these major causes which result into band broadening be eliminated? Yes. So according to her, these causes can be eliminated. How can they be eliminated? Let us consider only the multiple path flow or eddy diffusion. Did you join late? Huh? So you didn't attend my earlier lecture? So I think in a group of about 80, 90 people, unanimously we said that these causes cannot be, can never be eliminated. What can we do about them? We have to optimize them, right? Yeah, please. You will frame a question. I'll give you one. And you are, yes, you are next. Yeah. Introduce yourself. Come here. Why are you introduced?
I'm Saili Moite from doing MSc Part 1 Bioanalytical in Kazakh.
What was I? What does, or let us say, why capacity factor is also called as retention parameter. Why? It is called retention parameter, is it not? Because it is related to the retention of solutes on the stationary phase. But why K dash, which is capacity factor, is also called as retention parameter. Anybody? Yes, please.
Directly proportional.
Yes, but what does K dash plus, you have to say, what does K dash signify? The magnitude of K dash signifies whether a solute will remain for a longer period of time or shorter period of time. It means K dash is indicating the retention of solutes on the stationary phase, and therefore K dash, which is capacity factor, is also called as retention parameter. Right? What are the, yes, question ready? Okay.
Reasons why gas chromatography is used to separate the gases.
Why it is used? Can you frame it a little better? But that we don't know, no? We have not made comparison. What she said, that question, why gas chromatography is used more than liquid chromatography? So we have not compared so far. We have just introduced the theory of, please sit down. We have just introduced the theory of chromatography and then started with BC. We have not touched LC. So, why gas chromatography is one of the popular techniques of separation? Is it not? And then you have all those attributes, that it is fast, it is sensitive, it is reliable, and it is versatile. So the question should be, why gas chromatography is one of the popular techniques of separation? Number one should be, answer should start that it makes us possible to separate mixture of solutes in the gaseous phase. That is the best advantage. And then you say these are the attributes which make it very popular. Am I right? Khalsa, 14, 1-4, yeah, stand there only. Don't come. You want to frame a question or you like to answer a question? Answer. Why? Framing question is difficult, isn't it? Anyway, we have done the theory of chromatography, right? Why do we want baseline separated peaks? As a chromatographer, why do I require baseline separated peaks?
Because we get the accurate band.
What is the aim of a chromatographer? Basically, separation plus what she said is qualitative analysis and quantitative. So if there are overlapping peaks, then some degree of precision and accuracy is lost in determining the retention time and calculating AUC. Correct? And therefore, we need not overlapping peaks, but baseline separated. Now one more. Why are they called as baseline neighboring peaks? What's the reason for that term, baseline? Anybody? Volunteer? Because after separation, after elution of the first peak, the detector touches the base. It means zero is gone. Before the second solute is starts eluting. Therefore, it is called baseline separated peaks. Okay. Yes, you introduce yourself.
I'm Rajiv. I'm doing MSc Nutra from
Also, okay. Now, what have you understood in the theory of chromatography about N? What do you understand when I say in chromatography? What is N, capital N? It is the number of put it. It's not complete. N is number of theoretical plates associated with given length of column. Otherwise, if you don't specify the column length, it becomes vague definition. Just as I said, what is a chromatogram? Yes?
It is the plot of detected response versus time in a chromatography.
Chromatographic separation. Definitely chromatography is fine because chromatography is separation, but better it is that way. Chromatographic separation, right? Okay. What is meant by liquid phase loading?
Loading with the mobile phase, the solute which we prepare by mixing it with the percentage of that, like solute is 5% loading. That is, we can do the loading from 2% to 20%, but it is
The same one, no? There is some state like Uttar Pradesh, and there is one district, and then you have to be specific. Don't get disheartened. I am here to correct you. Okay? See, we have said that liquid phase loading, yes, varies from 2% to maximum 20% generally. But what is it? It is the amount of a suitable liquid coated on 100 grams surface of inert solid support. Correct? Okay. Continuation of that. What will happen if you prepare a stationary phase with 0.5% liquid phase loading? According to you, what will happen? Instead of 2% minimum, I want to 0.5% loading. Any guess? Get that? Yes, in a way you are right. But compared to 2%, retention time will decrease. Why? Because most of the surface may not have enough coating. And in fact, I am not explaining to you this, if the coating, liquid phase coating is less than 2%, correct, most of the surface remains uncoated, major part. So there will be two types of processes for separation. One will be adsorption, which is on the free surface, and one will be partitioning. You get my point? And we want the separation by partitioning only. And if we want only partitioning to be responsible for separation, then the entire surface has to be uniformly coated. And that is found that if you have 2%, it is done, and as it increases more and more, liquid phase is available for interaction. So your answer in a way is right, that if it is 0.5%, K dash will be less, but then the right answer, supplementary answer will be that when the liquid phase load is very low, there is bare surface of the stationary phase particles, and therefore adsorption and partition both play a role, and we are not sure which is causing the same. Right? Tu Vira, introduce yourself.
Hello, my name is Shruti Sawant. I am doing MSc Partner in Bioanalytical Science in Khalsa.
Okay. Now, would you like to frame a question or answer a question? Answer it. Okay. There is classification of adsorbents as weak, medium, and strong. What is the basis of this classification? On what basis they are separated as weak? Some of them are weak, or some are moderate, some are very strong.
It depends on how much it can absorb on its surface area.
AB or AD? Absorb or adsorb? That is there, but how do I classify? Every adsorbent will adsorb on its surface solutes. Otherwise it will not be called as an adsorbent, right? But I have 2 or 3. Where do I put 1, 2, 3 into these 3 classes? Moderate, weak and strong. Any volunteer? Yes, please.
So weak absorbents will edit the solute faster, and strong absorbents will give time for interaction and
In a way, but your answer is still not complete. Yes.
You treat them with Brockman and shot. You treat them with a dye. If the dye elutes out quickly, then the adsorbent is weak. If it elutes out very late, it is strong. And in between, then it's semi.
Correct. So there has to be comparison, no? How do you compare? There is reference point, therefore. Right? Now, if you said you have got 75% marks, simply say 75%. She said 85%, without referring to what examination you have appeared for. If it is MSc Bioanalytical Sciences, there could be comparison. That she is better than you. But you have at BSc level 75, she has 80% as MSc. Can this be compared? No. So we take adsorbents, series of adsorbents, fill them in tube and pass specific dyes, colored dyes through them. You use the same mobile phase, maybe ethanol or whatever it is, common for all, and then determine that one retains these dyes for a very short period of time. It just weak, some moderate, and then some very strong. Correct? So with reference to adsorption of certain standards, and these standards in this case are taken as some dyes, colored dyes, then that classification is made. How would you choose? How would you choose? Yes, a stationary phase for separation, liquid stationary phase for separation. Maybe liquid chromatography, or just we have seen gas chromatography. But we have to choose a liquid phase, stationary liquid phase. Maybe wrong, doesn't matter, I am there to correct you, don't get scared at all. These are all our friends. बरोबर का चूक है बाबा? तुझे शत्रु है? नहीं. तुम्हाला काय प्रश्न विचारशील? मी ज्यावेळी तुला सांगतो की प्रॉपर लिक्विड फेज तू कशी लिक्विड फेज कशी चूज करशील, तर तुला काय प्रश्न पडेल का ताबडतोब मी तुला मला विचारावंसं वाटेल. Yes. So what your question should be? Okay, I will choose the proper liquid stationary phase. Tell me what is the nature of solutes? Are they non-polar? Are they semi-polar? Are they polar? Right? And depending on that, you will choose. Suppose I say that my solutes are polar in nature. Now, what type of stationary liquid phase you will choose? Huh? Why? Light dissolves light. And unless solutes interact with the stationary liquid phase, there cannot be separation. Right? If you use a non-polar for polar, all polar solutes unretained will be eliminated as a single band without any retention. Now the factor which governs K dash, one of the factors is eluting strength of mobile phase. Stronger the mobile phase strength, shorter is retention time. But what do you mean by eluting strength? Yeah. Is it polarity of the mobile phase, or is it something different when you consider eluting strength of mobile phase? Which one is stronger, which one is weak, and which one is huh? Forgotten?
No,
Huh?
I can't understand.
Okay, okay. When in chromatography we say that eluting strength of mobile phase is one of the factors which governs K dash value, capacity factor, right? So I would like to understand, what do you mean by eluting strength of mobile phase? Yes? No, mobile question. Good listener. My question is, what do you understand when I refer to the term eluting strength of mobile phase? Yes?
Ability to carry
Yes, yes. What?
mobile phase will pass that solute faster from the column. That shows that it is a strong eluting strength. If it will take time more, it is weak.
So if I say now, yes, if I say that eluting strength of mobile phase means its ability to take solutes through the column or through the stationary phase, if it is able to take faster, eluting strength is higher. If it is able to take slower, the eluting strength is lower. But what determines the eluting strength of mobile phase? Yes? Nature of the solutes. So for non-polar solutes, the mobile phase is strong. For polar solutes, polar mobile phase is strong. For polar solutes, non-polar solvent is weak, and for non-polar solutes, polar is weak. Is that clear? And therefore, it has the eluting strength of mobile phase has nothing to do, absolutely nothing to do with the polarity of the solvent. It all depends on what is the nature of the solutes in a mixture. Is that clear? Okay. Who will volunteer now? Who will volunteer for the early part of our discussion? Before GC. Before GC. Can you narrate me the story which I narrated you in the beginning today? And what is this? Anybody, any volunteer? Yes, anybody? Please raise a hand. I started with a story now. An incident happened in the UK. What is that? Are forgotten? Okay, what is the moral of that story? Freedom always comes with accountability. It cannot be without accountability. Right? Now you ask me questions. Quick, last 5 minutes. Today we'll finish that. Nutraceutical number 7. Who's this guy? Who is? 7? हां बरं दादा कोणाला असं ओळखीचं नसलं म्हणजे परत 7. You ask me a question. Now all in next 5 minutes you ask me question. So framing of question. Yes. You want 1 minute?
Yes.
Okay. So anybody who is ready with a question? Yes. What? Yes.
Sir, from this only to others.
Okay, quite good.
What do you feel which chromatography to be used now? If you have done many of chromatography, which chromatography you feel?
Which techniques you?
Which is convenient, gas chromatography, which is convenient for you?
Okay. Now her question is, given a choice, right? Which one will I use as my first preference? Huh? There is nothing like first preference or second preference. First, I will ask, what is the nature of sample? Okay. Now you will say that it's a mixture of solid solutes. Then I will ask, are these solids volatile enough? Okay, you said yes. I have not made decision yet. Are they soluble in organic solvents or in water? Is they in organic solvent? What degree of accuracy you expect? Is it not? You are given a mixture, what degree of accuracy you require for its qualitative and quantitative analysis? If it is plus minus 2%, let us say, then I will say TLC, thin layer chromatography fast. But if you want a very high value, then I will go what? Gas chromatography, because you said they are volatile. Then I will also ask you, what is the quantity of sample available? If it is large quantity available, I put on the column. It may take maybe 4 hours, 5 hours. And if your degree of accuracy required is not very high, the quantity of sample is more, naturally I need not go in for GC. So there is no simple answer. In fact, one full lecture I am going to devote for selection of an appropriate analytical method. And many times, you youngsters, after getting exposed to liquid chromatography, gas chromatography and so on, you have only one mind, one track, like blinkers in the horse. What method will you use? GC, LC, TS. And why? There are no other methods. Therefore, the correct analysis or correct choice of an analytical method will depend on the entire history of the sample and the different questions which I have prepared already. And we'll discuss that in the class. These questions are to be asked, answers are to be written, and then think seriously. Oh, this. Okay. Then still you will have 2-3 alternatives. From that you can choose them. For example, I'll give you a simple example. You are given aspirin tablets or salicylic acid derivative. Right? So it's an organic acid soluble in water. I give you 10 tablets and I ask you to calculate what is the content of salicylic, that aspirin, per tablet. So what you do? Mix the 10 tablets, make powder, dissolve in water, dilute to 100 ml, let us see. Then what? Which method will you use? Huh? Volumetric, correct. Why? Because enough quantity is there, water solubility, it is an acid, so I can use a strong base and use an indicator like phenolphthalein. I don't have to go to colorimetry, because quantity of aspirin is more. Okay, the last one.
So what are the ideal characteristics of carrier gas?
ideal characteristics means they, as we have carrier gas, they should be inflammable, safe, inert, chemically inert as we said. It has to be dry and it has to be free from impurities and moisture. And it should be readily available at reasonable cost. That point I have not discussed because helium, I have shown, please, helium, I have told you, is used as a carrier gas. But where is the availability of helium cylinders in India? That they are very expensive cylinders. Helium is very expensive carrier gas. And therefore, choice how to choose a carrier gas in gas chromatography is the right question. When you have neon, you have rare gases and also nitrogen and hydrogen. Nitrogen in our country is available in high purity in plenty. It is a very cheap gas available. Hydrogen cylinders are also available, but because of its limitation of combustible nature, we try to avoid it as far as possible. With argon, yes, in specific cases, argon is available in India. It's slightly expensive than nitrogen, but still a useful carrier gas. Helium, as I said, is very, very expensive in nature, and it's only highly specific analysis and separation in gas chromatography, helium used as a carrier gas. But you will ask me, advantages or disadvantages of these rare gases. And I have given you a table, which we will copy, of the thermal conductivity of these different gases. And we are going to discuss that detector. So thermal conductivity sometimes of these gases determine the choice of carrier gas. And therefore that will be our discussion tomorrow as to how to choose an appropriate carrier gas, just as we have seen how to choose an appropriate liquid gas. Right? Thank you.